Okay. So it is a great pleasure to introduce our next speaker, Professor Jan Musson from University of Wisconsin, and he will tell us about Weyl, groupoids, Young diagrams, and Borel subalgebras.
Hello, yes. How do I share my screen?
Yes, please.
How do I share my screen? Can you hear me?
Yeah, press green button, share.
Uh, oh, sorry. Green button. Ah, right. And
And then choose your presentation, your window with presentation.
this one, I think. Yeah, okay. Can you see it? I'm talking about Weyl groups, young diagrams, and Borel subalgebras. But first, I want to thank the organizers for the invitation to speak and for this wonderful conference in difficult times. So this is mostly combinatorics of young diagrams and partitions. So partition is the descending sequence of integers, and I call these the entries the parts, and identify the partition with the young diagram that it defines. And then what I want to consider is given two integers m and n, you let X be the set of young diagrams that fit inside the bottom left corner of a rectangle with n rows and m columns. So about my conventions for young diagrams, the bottom row has lambda 1 boxes um, and so on. Oops. Right, now I have a slightly unusual way of labeling the rectangle, which you can see by looking at the diagram right at the bottom. The rows are labeled epsilon1, epsilon2, down to epsilon n, and the columns by delta1, delta2, and delta3. So the individual boxes in this array are labeled by differences, epsilon I minus delta j. So that's how I'm going to refer to a box. The box in row epsilon I and delta j is called B epsilon minus delta j, or sometimes just box epsilon I minus delta j. And we're going to say that a box uh, or a box is an outer corner of lambda if B is not contained in lambda, and adding B to lambda creates a new Young diagram. And it's an inner corner of lambda if the box is inside lambda, and removing it creates a new Young diagram. So these are fairly standard ideas. Then I let X alpha be the set of all diagrams that have box alpha as an outer corner, and X minus alpha, the diagrams that have uh, B alpha as inner corner. Then there's a bijection between these two sets obtained by adding or deleting a corner. There are various ways to describe Young diagrams, apart from this. One of them is a word in of length m plus n in the alphabet RD. And the idea is the upper border of lambda in X is a connected sequence of line segments starting at the left corner and ending at the bottom right corner. Each line segment carries the label R or D according to whether it moves to the right or down. Okay, so W is then the sequence of labels. And I'm going to let curly W be the set of words consisting of MRs and NDs, and then there's a bijection between these sets, which is given, by reading the word associated to the path of the diagram. So first question is, what are the operations on words that correspond to adding and deleting boxes? And so here's an example where N and M are 2 and 3, and I draw the rectangle with faint lines and the Young diagram in bold. So on the left, you have the empty diagram. And if you read the path, the 2 down steps and then 3 R's, and there's only one outer corner. So if I add that, then the new path has word D, RD, RR. So it's clear, I hope, that what happened was I switched a DR to an RD corresponding to the box that was moved. To say a bit more about this question, what are the operations on words that correspond to adding or deleting boxes? We need shuffles. So these are certain kinds of permutations. Sim I is the group of all permutations of 1 up to n and 1 prime up to m prime. And in one line notation, sigma is sigma of 1 and so on. And the set of shuffles is the all permutations where 1 up to n and 1 prime up to m prime occur in order. They are subsequences of sigma. Okay, so from any word, you can obtain a shuffle, reading left to right, replace every D by the smallest unprimed integer and every R by the smallest primed integer. So the words we had before were DDRR. The D's are replaced by unprimed integers. So you get 1, 2, 1 prime, 2 prime, 3 prime, and DR, DRR. You get a different shuffle. Then if you have a root alpha, which is epsilon I minus delta J, you look at all of the words which have I and J prime as consecutive entries in the shuffle, and then you define bijections by interchanging these 2 letters in the words. And there's also a bijection between shuffles and X that can be defined. The kth step is D if sigma of K is in 1 up to N, and otherwise it's R. And then you have a commutative diagram of bijections. From any Young diagram, you can read off a word gives you a shuffle, and a shuffle gives you a Young diagram. I want to talk about the Lie superalgebra GLMN. This is the set of all block matrices of the form X equals A, B, C, D, where A is n by n and D is m by m. And G0 consists of everything with entries off the diagonal. G1 plus is everything in the upper right corner, and G1 minus in the lower left corner. Then the sum of these 2 is a Z2 graded associative algebra. So G becomes a Lie superalgebra in the usual way. And SLMN is the subalgebra where the trace of A is equal to trace of D. Then you have the usual terminology. H is the subalgebra consisting of diagonal matrices, and for a root alpha, you can define the root space. the root spaces. Then the set of roots of, we'll be interested mainly in the set of roots of G1 plus and G1 minus. The set of roots of G1 plus are epsilon I minus delta J, and the negative roots are minus these. Okay, so yet another way that Young diagrams show up is with Borel subalgebras. So B0 is the set of Borels whose even part consists of upper triangular matrices in G0. So for the moment, just look at the diagonal blocks, right? And then you have some other stuff. And the other stuff is given by a Young diagram. So this small diagram here with 3 rows and then 1 row, well, you put that in the upper right corner, except that you, for the boxes in the diagram, you put 0 and star everywhere else. Star means an arbitrary entry. Then for the lower right, the lower left corner, you take the transpose of this diagram and this time interchange stars and zeros. So that will give you a Borel subalgebra in B0, and they all look like this. So this is best expressed in terms of groupoids. A groupoid is a small category with all morphisms invertible. And the objects of G are called the base. For a set X, the symmetric groupoid on X has base consisting of all subsets of X and morphisms or bijections between subsets. So if X to Y is a bijection of sets, then there is an induced isomorphism between these symmetric groupoids. And we say that the group X on X, if there's a functor from G to S of X. This is the analog of permutation representation of a group. Now, suppose that we have a commutative diagram of functors on the left side, the groupoids are equal, but we have 2 functors to do 2 different symmetric groupoids. And tracing it round, it means that omega f of gx is E of G applied to omega x. So we're interested in that. And in the transitive situation, we say that omega is an equivariant bijection from X to Y. And now I'll introduce 4 groupoids. Let's start with the second one. This is the first groupoid that I introduced, where the base is X alpha, the set of Young diagrams containing box alpha, and the non-identity morphisms of these T alphas. And then below that, you can do something similar for words, and the non-identity morphisms here exchange 2 consecutive pairs dr, and there's a version for the Borel subalgebras, and the one at the top is a sort of abstract version with generators, where you tell you what the generators are. The base is all isotropic roots, and the non-identity morphisms turn alpha to minus alpha. Then I've set this up so that we're doing corresponding, we have isomorphic sets, and we're doing corresponding things to each of them. So we have a commutative diagram of bijections like this, and that leads you to a commutative diagram of isomorphisms of groupoids, because all I did was change the names of the objects and morphisms. So clearly, this is obvious. Now, I want to study groupoids in the affinization of SLNM, and this requires some new ideas. One of them is rotating words. So if I have a word in n plus n letters, I can just take the first one and move it to the end. Okay, so we have something that goes on with words. What is the corresponding operation for Young diagrams? So I define two subsets of X, the row full subsets, where the first row, the bottom row, has as many entries as possible, M, and R empty is where the top row is empty, right? And then we have bijections between these two sets. So the idea is if lambda is full, then you can take something away from it. So I take away a row, minus, that's why the superscript is minus row. And if mu is empty, then I can add a row. And these are two mutually inverse bijections. Yeah, and you can do the same thing with columns, but I won't spend time on that. And there's a bijection between X and W. And so here's my question again. What is the corresponding operation on words, on Young diagrams? And the answer is if the first letter of W is D, add a row. And if the first letter of W is R, remove a column. So that's case B, I think, where the first letter is D, and in W of lambda in the word, and in this case, the word with the this is very easy to see if you just draw a diagram. The word of lambda plus R is XD. And now we introduce a equivalence relation on X cross Z. Lambda K is equivalent to lambda plus R K minus M if lambda is empty, and another one involving columns. And we look at the set of equivalence classes, and I call that X cross Z. The poset X is graded. It's a famous poset where the degree of lambda is the number of boxes in lambda. Now, there's a degree on X cross Z where the degree is number of boxes in lambda plus K. And this degree is constant on equivalence classes. Adding an outer corner to a Young diagram increases the degree by 1. So here's an example just to get used to this. Here, N and M are 2 and 3, and I want to know the equivalence class of this Young diagram with a 3. So I'm looking at pairs, Young diagrams, and integers, and I represent the integers as a superscript. So what you can do, all you can do is add a row or delete a column, right? So starting with this one with 2 boxes, then you get a square, a rectangle. Now you can add no more rows, but you can delete a column. No, you can delete a row, delete another row, and then you get the empty diagram. And to this, you add a superscript, so the total degree is 5, always 5, all right? And in general, every equivalence class has size m plus n. Well, there's a theorem, not very easy to prove, but there's if m and n are co-prime, there's a functor from this abstract groupoid I to symmetric on x cross z, which gives you such that there's an embedding of graded posets, and this map is compatible with the action of the groupoid. Oh yeah, and if we have a bijection, we had a bijection between x and b0, then you get a commutative diagram of groupoids and functors. Here's an example that I hope will help. This is the graded poset of Young diagrams that fit inside an n by m rectangle. You make it bigger by adding a box. But I've constructed this new poset, which contains the original one, by using these equivalence classes. And you see it's infinite in both directions, but periodic. So the part in degrees 0 through 6 determines everybody else. Okay, so I want to talk a little about Kac-Moody superalgebras. The input is a matrix B and a subset of R, and the output is a Lie superalgebra. You get some generators E, I, F, J for every J in R, and an abelian Lie subalgebra H. And here are some of the relations. My time's running out, so I won't read them. And these relations define the so-called half-debate algebra. And the algebra that we're really interested in is a factor of this. But by some miracle, we don't need the other relations. So I assume, excuse me, the M and N co-prime. And then earlier we studied Borel's in GLMN. We could have studied Borel's in SLMN. For every word or partition, we have a Borel subalgebra and a Cartan matrix of size R plus R. And now, and here are the generators. And to form the affinization, you go in 3 stages. You first form the loop algebra by tensoring with a Laurent polynomial ring, and then you form a central extension of this and a derivation. And the Cartan matrices are related in the following way. A0 is a matrix for the finite Lie algebra, and I add another row and column to this. Oh, I always assume that my matrices are symmetric. So I add V and V transpose, where V is so that the row sums and the column sums are equal to 0. But then you realize you could have done it in a different way and taken A0 underline to be the matrix in the upper left corner and done it that way. So the theorem is that you can get SLMN in this case, and we have 2 algebras defined by 2 matrices. They're both isomorphic to SLMN, and they both have the same affinization. Oh, some technical stuff I'll try to skip. But I want to talk about extending, I do have to talk about extending Borel's. We say that the Borel subalgebra of this affinization, L hat G0, is the extension of a Borel with simple roots pi 0. And there's an additional root, the extending root is delta bar minus theta, where theta is the longest root. So it's completely determined by the input data. And I guess this is the important theorem. Two pairs in B0 cross Z are equivalent under my equivalence relation if they both extend to the same Borel subalgebra. And so the Dynkin diagram of the affinization has m plus n nodes, and a priori you don't know, if you're just given one of those diagrams, you don't know which finite algebra it came from, but there are m plus n possibilities, and each equivalence class I mentioned before has size m plus n, and that's why this turns out to be bijection. I think I started a bit late, so here are some quick examples. So I have these two shuffles, and don't just look at the first column, because if you read off the shuffles 1 prime 1, 2 prime, 3 prime 2, this gives you this Dynkin diagram, Katz-Dynkin diagram, and there are two examples. So that's the first column. In the second column, I bend up the diagram in the first column and add an extra root. The second column gives the Dynkin diagrams for the affinizations. And the third column gives the Dynkin diagrams. Well, what we do next is delete the node to the right, the rightmost node, and unwrap it again. And if you just look at the symbols, there's a gray, and white node, which is what you get by deleting that rightmost node. Last thing, let's consider the rows. If the shuffle corresponds to the Young diagram lambda, then the shuffle in the third column corresponds to deleting the bottom row. And there's a compatibility with odd reflections. In the first column, the second diagram is obtained by an odd reflection using the second node. And in the third last column, the two are related by an odd diagram using the third node. So, there's one other case where the same combinatorics arise is in relation to deformed quantum Calogero-Moser systems, but I don't have time to give that. Thank you.